Okay, kids, so we're back here, section 4.2, a little bit of review, a little bit of something new. Uh, Kinetic energy, studied that in grade 11. There's a symbol, EK, energy of motion. If an object has motion, it has an energy associated with that motion called kinetic energy. Then a little something new, the work energy theorem, which is very closely associated with this. Very closely associated with this. So let's put our our imagination to work here, and let's imagine an object right there. Okay, and this object has a mass m. That's the mass. And let's say it's like all by itself, so far away from any other mass in the universe. So maybe it's like in between galaxies. So the closest real mass that it could possibly ever get any force of gravity on is so far, far away that it's practically zero. And then let's say that a force is applied to it. Okay? Now you may be asking, how is that force applied to it? I don't know. Maybe a superhero, Superman, the Silver Surfer, I don't know, pushes on it. Somehow there's a force acting on it. Remember, we're using our imaginations here. And let's say that when the force started acting on it, the object was at rest. Okay, the object was at rest. And then the object moved through some displacement. Now, we're not going to use x or y here because we're in the middle of nowhere. So we're just going to say it moved through some displacement. So that when the object is now here, it has a final velocity that isn't known, but it's some value. I don't know what it is, 10 meters per second, whatever it is, right? So if you remember back to grade 11, we could investigate what that final velocity is. We could try to calculate for it by using this equation right here, which is a rearrangement of one of our 5 equations of motion. But I put it in this format because it's very convenient to be in this format. Now that term right there, it disappears because, well, the initial velocity was 0. So we're left with just final velocity squared is equal to 2 times the acceleration of the object, all times its displacement. Now, what we're going to look at right here is, since this is the only force acting on it, that force, that's the only one acting on it, by default, it becomes the net force. There are no other forces acting on it. And what we can now do is calculate the work done by that force, and therefore the work done by all forces, the net work, by using our friend, the scalar product, the dot product that we've seen in the past. Right there. And we know that this is the magnitude of that force times the displacement of that force times the cosine of the angle between them. And if you take a look here, the force and the displacement are parallel to each other, so most definitely theta is equal to 0 degrees. And cos of 0 is 1. There you have it. There's the work, which, as I said before, since it's the only force, I can replace that with Fnet. Not a problem. I can replace that with Fnet. But I also have to remember Newton's second law. Let's not forget Newton's second law, which is the net force acting on an object is equal to the mass of that object multiplied by the acceleration that object is undergoing. So I can put that in there. How do you like them apples? You like apples? How do you like them apples? There you have it. Okay, there you have it. Now, since these are all magnitudes, I'm just going to write ma, which will be the magnitude of the acceleration, and delta d, which would be the magnitude of the uh, displacement. Magnitude of the displacement. And now what we're going to do, we're going to go back to this equation here, and I want to find the magnitude of both sides. So I'm only interested in the magnitude of these now. Okay, so I'm going to take the magnitude of both sides of the equation. There you have it. Well, look, what we have here is acceleration times displacement, magnitude multiplication, acceleration times displacement, magnitude uh, multiplication. So there's a commonality here. So let me rearrange this. And we'll get VF squared. Oops, got to drop the magnitude, made a boo-boo there. Let me fix that. VF squared all over 2. So VF squared all over 2 is equal to magnitude acceleration times magnitude of displacement. This is all magnitude. Well, look what I have here. Acceleration magnitude times displacement magnitude is the magnitude of the final velocity squared all over 2. So, oops. So I can replace that right in there. A delta D becomes VF squared all over 2. So we have found the work that this force, and therefore since it's the only force, the network that's done on it, right there. And since the object has sped up, it's gotten faster, we know that work is equal to change in energy, right? We know that work is change in energy, and the energy that's changing is kinetic energy. And what I'm going to do is I'm going to subtract 0 from this, because subtracting 0 from it does nothing. And what people like to do when they do proofs to try to show something to someone is I'm going to rewrite 0 in a different way. Look, I'm going to rewrite 0 like that. Because if the initial velocity, or at least the magnitude of it, well, if it was 0, that's 0 in here, the whole term is still 0. The whole term is still 0. So then I can come to a conclusion. Look, this can be my expression for kinetic energy final. This is my expression for kinetic energy initial. And that leads to me making the conclusion that in general, I have an equation now that will work for any velocities, initial velocities, final velocities, velocities in between. If you ever want to find the kinetic energy of an object, it's half its mass times whatever speed it has squared. And we've derived this equation. We've derived this equation. So here is an example. I have a 1,000-kilogram car, accelerates from 15 meters per second, 25 meters per second in 10 seconds. Calculate the work done as the car accelerates. So you want to draw a free body diagram of the car. That would be the applied force that the car gets from its wheels as the engine is moving and the tires are moving. There would be the force of gravity, right? Which is also known as the weight. There would be the normal force, and since this is on, we're assuming a flat surface, let's assume that it's negative force of gravity, which isn't true, as you now know, if it's on an incline. And then there would be maybe frictional forces from the air, from so many other types of frictional forces with the mechanism of the car. So all those forces together, they will do a work on it, the net work done on it, and what we want to do is calculate that. But as you take a look at this car, it's on the road, We're going to assume a nice flat road, so there's no incline or going downhill or uphill. So all the work that's being done on this is kinetic energy change. We're assuming no other energy changes come into play here, which would equal kinetic energy final minus kinetic energy initial is equal to half the mass final squared, half the mass initial velocity squared. So you've seen that equation before. Well, let's do some factoring here. Factoring's always fun. There, oops, don't want to put the vector sign in there. Almost made a big boo-boo. It's not a vector. We're all in magnitudes here. Almost made a boo-boo. Okay. And now we can substitute in and we get an answer 2.0 times 10 to the 5 joules. So you've done an example there. Perfect. Perfect. Okay, so this is all related to work energy theorem, showing the association between work and energy, and it says the total work done on an object equals the change in the object's kinetic energy, provided there is no change in any other form of energy. So, like kinetic energy is the only one that we are going to be looking at in using the work energy theorem. So if there's a change in another type of energy, then this doesn't apply. And I'm going to show you that in an example coming up. So here's a situation. There's a skier on this hill here. Let's say they have a mass M. And when they're at this spot right here on the ski hill, they have some initial velocity. And they're going to ski down the hill. And here we got the X and Y coordinate system set up. They're going to ski down the hill so that they go through a displacement we're going to call delta X, right? And the angle here on the hill is theta degrees. So that means we got 90 degrees down here when we draw the force of gravity acting on the skier, right? There's 90 degrees between the force of gravity's direction and the horizontal. And that means the complementary angle will be phi right in here. And we're going to use the work energy theorem here in the hopes that we can calculate what the final velocity is here. Now the work energy theorem has to be respected, and when you use the work energy theorem, you're saying there are no other energy changes other than kinetic energy. So we have to incorporate the fact that there is gravity here. We have to incorporate it by the force as opposed to there being a change in gravitational potential energy. So it's a bit of a nuance here when using the work energy theorem. So work done by the force of kinetic friction would be the magnitude of the force of kinetic friction times the magnitude of the displacement, let's change that to an x, that the object undergoes, this case is the skier, magnitude that, times the cosine of the angle between them. Well, displacement's down the hill, force of kinetic friction is up the hill, that's cos of 180 degrees. Plus, if we want to find the work done by the normal force, it's normal force, magnitude, displacement magnitude times the cos of the angle between them. Well, displacement is down the hill, and normal force is perpendicular to being down the hill, so that's the cosine of 90 degrees. Plus, Work done by gravity would be the force of gravity's magnitude of the displacement times the cosine of the angle between them. Well, displacement is down the hill, force of gravity straight down, and we've said that that is phi, the complementary angle to the angle of the hill, and that will equal change in kinetic energy right there. Well, this would then equal force of kinetic friction, delta x, just the magnitude. Cosine of 180 is -1, so that means we put a minus sign out front there, plus the magnitude of normal force, delta x. Cosine of 90 is 0. So really, I don't even have to worry about that term. That whole term is gone. Then magnitude of the force of gravity times the magnitude of the displacement times cos phi is equal to kinetic energy final minus kinetic energy initial. So that leaves us with minus force kinetic friction multiplied by displacement, magnitudes only, plus force of gravity, that's magnitude, times magnitude of displacement, times the cos of phi, that complementary angle, is equal to, um, well, let's do, before we say equal to, let's bring the initial kinetic energy over to the other side, so that becomes plus kinetic energy initial is equal to kinetic energy final. And we can rewrite the beginning part of this. We're going to rewrite the beginning part of this. And then plus half mass initial speed squared is equal to half mass final speed squared. So we're going to do a little bit of final rearranging here. A little bit of final rearranging. And that'll give us final speed squared, and you can from that calculate what the final speed is. So here's where you use the work energy theorem, right? And we're saying, look, I know there's a gravitational field here, I get it, but if I'm going to use the work energy theorem, the only energy that I have to account for changing is kinetic energy, and gravity is taken care of by the work done by gravity, by the work done by the force of gravity. So that's an interesting situation. So now we're going to look at gravitational potential energy near Earth's surface. So this is something we looked at in grade 11 as well. So here's the ground right here, okay? And we've got an object that's being lifted upward by some force, and there's still a force of gravity on it. So the object would start on the ground, and so that would be its initial position there, and end up there on the ground. That would be the final position when someone stops moving it. But what we want to study isn't this whole motion. I'm only going to be interested in the motion between here and here, right? So let's call this this other one y final prime, y initial prime, because I'm not interested in those. I'm only interested, yes, it actually started here. Yes, it actually ends there, but I'm only interested in this part right here. Okay? And this part right here will have its own y final and y initial, right? Y final will be there for our purposes. Y initial will be there for our purposes. I know there's these other spots before and afterwards, but I'm not interested in that part of the motion. I'm only interested in this part of the motion. Why am I saying that? Why am I going on all that trouble? Because in the red part here, in that part of the motion right there, I'm going to say that the acceleration is equal to 0. I'm not worried about it starting, not worried about it ending. I'm only worried about the part in the middle where the acceleration is 0, meaning it's moving with a constant velocity. And what we're going to do here is realize that if the acceleration is 0, that means there's no change in speed, no change in velocity, that there will be no change in kinetic energy. Whatever velocity it had right here is the same velocity it had right there. So why am I saying that? Because I want to ensure that whatever work is done here, yes, it's going to change energy, but the only energy that will change is gravitational potential energy. And I hope you remember that was the symbol we talked about in grade 11. So let's take a look here at what's happening. Let's take a look here at what's happening with the forces that are being applied here. So if we want to calculate the work done by the lift force, it's going to equal force lift dot the displacement it goes through, right? We looked at that before. So this will equal the magnitude of that lift force times the magnitude of the displacement times the cosine of the angle between the displacement and the lift force. Well, kids, the displacement is straight up and the lift force is straight up. So theta is 0 degrees here. Theta is 0 degrees here. So that becomes magnitude of the lift force times magnitude of the displacement, because we all know that the cosine of 0 is 1. And then since this object is being pulled with no acceleration, we know that the lift force and the force of gravity are equal in magnitude but opposite in direction. So I can make this substitution. It's the same quantity, just different sign. And that would equal negative mass of the object times the gravitational field there times delta y. There we have that. But since it's all in magnitude signs, I can just write mg delta y. So the work done by the lift force, the only energy that's been gained here is gravitational potential energy, which would be gravitational potential energy final minus gravitational potential energy initial is equal to mg. Now instead of having delta y, I'm going to have y final minus y initial, and I can rewrite this as mg y final minus mg y initial. And now I can say, look, I can see a pattern here. This is the equation come on, there we go, change the color. This is the equation for the final gravitational potential energy. This is the equation for the initial gravitational potential energy. So I can say in general, if you want an equation for gravitational potential energy, it's just mg y, wherever it is. So this is an equation we had in grade 11. We use an h instead of a y, but nevertheless, there you have it. So here's an example. Here, kids. Calculate the change in gravitational potential energy as Mr. Z drops from the countertop, you know, the countertop at the beginning of, at the front of the class, to the desk. There's also a desk out there. Now, when you do gravitational potential energy, you have to say, well, where's going to be your 0 point? It's relative, this gravitational potential energy, right? It's a relative quantity. Where is your 0 point? So what we're going to do in this question is we're going to say the ground, that's y equals 0, right? The desk, that's y equals a height of 0.76 meters. And the counter we'll say is y equals 0.94 meters. So Mr. Zafiro is going to drop from here to here. And we want to calculate the change in gravitational potential energy. So change in gravitational potential energy is gravitational potential energy final minus gravitational potential energy initial, which is mg y final, mass times gravitational field strength near the surface of the Earth. But notice there's no vector sign above this g. It's all scalar. Minus mgy initial, because energy is more of a scalar look at things. So there's no negative 9.8. It's just 9.8. Okay, let's do some factoring here. So we've done some factoring, and we get 72.5 kilograms times 9.8 newtons per kilogram. Notice I didn't put a negative sign there. And y final is 0.76 meters minus 0.94 meters. Okay, and it's definitely going to be negative 128 joules. So there you have it. We've gone through two sections here on kinetic energy and gravitational potential energy. Okay, have a great day. Bye-bye.